This video aims to give a brief demonstration and overview into the work that's been undertaken in a project called Remote Monitoring of Concrete Condition, or REMOCC. It's an Innovate UK funded project, reference number 100222647. The project is focused on the early stage development of a sensor for detecting the levels of stress in concrete that's been reinforced by the addition of steel fibres to the concrete mix. Let's start by having a quick look at a couple of concrete samples that have been taken to failure that have been reinforced by the addition of steel fibres. Here we can see where the sample has failed that the fibres are bridging the crack. Here is another example of a different type of fibre called a crinkle fibre that's been used to reinforce the concrete. The way that this approach that we're developing works is we're looking for changes in the magnetic properties of the fibre as the concrete is under stress, because if the concrete's under stress and it's attached to the fibre, the metal fibre will stress. When the metal fibre is stressed, its magnetic properties can change. It can have a change in its magnetic permeability, which is a measure of its ability to support a magnetic field. So we start with a magnetic core, round which we wrap a coil of wire. When we pass alternating current through the coil of wire, it will magnetise a magnetic core and we'll get a magnetic field that leaks out into the sample. Now, when this sample is concrete or air, where there are no metal fibres present, we see a pattern of magnetic field that goes from one pole of the magnetic core to the other. So let's consider for a moment what happens when we add a magnetic steel fibre into the concrete. The magnetic flux lines are drawn into the steel fibre until a point where the steel fibre is magnetically saturated. The steel fibre itself becomes magnetised and it generates its own magnetic field, as shown by these orange lines of magnetic flux. We now add a detection coil shown in green that's orientated in such a way that it's trying to pick up magnetic field lines that come up out of the sample surface, normal to the sample surface, and these are strongest towards the end of a fibre. So when using this device, we really need to try and locate where there's an end of a fibre close to the surface. In this rather simplistic view of where the magnetic flux lines sit, of course, in reality there is magnetic flux leaking from various points in the core. So even in the presence of no magnetic fibre, we still get some field picked up by the green detection coil shown here when there is no metal fibre present. So when we take a reference reading in there, we do see some leakage field that's sinusoidal, following the same pattern as the drive current. But when we are close to a fibre, what happens is we see a distortion in the signal that this detection coil receives. And we can see this in the two pictures here, for the sensor being in air and the sensor being over the end of a fibre in a sample. In the interests of simplifying the analysis and use of this sensor, we've developed what we call a distortion parameter. And this is basically a measure, as we can see here, of the difference between the signal we receive and the sinusoidal reference that corresponds to what the detector sees when it's just in air. So all we're doing here is seeing if we can give an unskilled user who doesn't need to be able to interpret the signals a quick and easy way of measuring the signal from a fibre, which will change with the application of stress. So in the experiments we've done, we've put a concrete sample into a compression test rig. Onto this sample, we attach a relatively low-cost sensor that's driven by some custom-built electronics. And the position of this sensor is chosen to be at a point where we know from previous measurements and doing a quick scan that we're sitting right by a point where there is a fibre near to the sample surface. We want the housing to be non-magnetic, so 3D printing the housing and the supporting material of the sensor out of ABS is an ideal material, and it's low cost. Customised electronics has been built just for this project. The box drives a current through the coil which generates a magnetic field in the first place. The signal from the detection coil is amplified in two ways. The first way, we're looking for the magnetic field that's emitted from the end of a fibre. Sometimes this is referred to as an ACFM type measurement or a BH measurement. The other thing we're looking for is very small signals associated with a phenomena called magnetic Barkhausen noise. It turns out that this is a slightly more difficult measurement to do, but it can give us a very good way of discriminating between the difference of when the stress we're looking at is either in tension or compression. A data acquisition card is used to collect the data from the in-house built electronic system, which is then collected by a computer and is signal processed for measuring both this distortion parameter and the magnetic Barkhausen noise signal. For now though, we're just going to focus on the distortion parameter because it's the easiest thing to see, the change in stress with the signal. So let's start by looking at the screen on the computer. This is more complicated than the final screen will appear. This is so that we can tell exactly what's going on and have some level of diagnostics doing a test. So there are three main graphs here and we'll explain what each one of these does in turn. If we look at the lower left-hand graph, that's a reference signal that's been stored in air prior to the sensor being attached to the sample. This gives us an idea of what our detection coil should be seeing in the absence of any magnetic fibres. The graph in the top left shows the signal that's received by the detection coil during an actual measurement, and what we'll see when we start to run the example is how this starts off as a sine wave but then quickly distorts in the presence of a metal fibre. And remember, we're measuring that distortion of this signal from the ideal sine wave to help us determine what the stress level is in the sample. And finally, the graph on the top right will plot two curves. One curve in red is a measurement of the applied stress on the sample, and the measurement that we'll see in white is the distortion parameter that's been extracted from the data so that we can get an indication and a quantitative measurement by calibration of what the stress is in the sample. So now let's look at what happens at the start of a test. As we start off, the sensor is in air, so the signal on the top left is the same as our reference signal, and it's not yet been distorted by the presence of a fibre. What we'll see now is that the sensor is about to be put onto the sample and by the fibre, and straight away we can see that signal in the top left has got distorted. That is what the signal looks like on the sample near a fibre. Once this is located in position, you'll see that signal become steady, and then the graph on the top right, which is a measure of the process signal that gives us a measure of the stress, we'll see that start to plot and scroll across the screen. So what we're about to see is speeded up by a factor of 8 times. The trace in white corresponds to this distortion signal parameter. The trace in red is a measurement of the stress from the Instron machine, which we're using to compress the concrete. So we increase the stress, and as we can see, that parameter increases as well. We get to a point around about 138 on the horizontal scale where we reverse the direction and relieve the stress. What we can see here is that we have a very good correlation between a quantitative measured value of this distortion parameter and the stress that has been applied to the concrete specimen. So to recap, we'd need a reference measurement at a particular place on that concrete sample to do this reliably and be able to come back to the same sample and get a quantitative measure of stress in that sample. There are, of course, many questions that remain unanswered and further work is required, but what we've got here is a demonstration of a first-of-a-kind principle that we can use these fibre reinforcements to measure the stress in a sample by the way that the magnetic properties of those fibres change. The REMOCC project team would like to thank Innovate UK for funding this project, and we'd also like to thank the monitoring officer Alan Harrison, whose help and support during this project has been greatly appreciated. We'd also like to thank Michael Mulheron from the University of Surrey, who, despite not being a formal member of this project, has provided some outstanding and very vital support and samples that have ensured the successful outcome of this project.